I think Nathaniel can allow others to record too. Can you try, Nathaniel?
Okay, let me.
Okay, let me try. No, the teacher who can do that, the professor.
I'm putting it for everybody. Oh, there can be only one co-host, is it?
No.
Oh, you can make as many as you want.
Okay,
I don't think so.
Ale
Yeah.
is already recording. Okay, that's good. Okay, one person, Nathaniel, is also recording. Okay, that's good. That's good enough. Okay. So either of you just put it on YouTube. Okay. So let's start. Today's lab is viscoelasticity. So by the time we go over the theory, hopefully MATLAB is already installed on your computers. By the way, there's several of you who are not here. Anyway, I think they will join soon. All right. Now, can you all download the zipped folder that I sent to you? The title is Viscoelasticity. I just emailed to all of you a zipped folder called Viscoelasticity. Can you please download that? And then let me share my screen. Okay. Please open this document. If you click inside, there will be a folder called Viscoelasticity. And in that, you will see a viscoelasticity.pdf. And please open that PDF file. So you will see this manual. So all of you got this, right? The zipped file. Okay, there is something on the chat. Yes, sure. Yeah, please take a few minutes, download that file, and maybe let me launch a poll.
Is it MRTSU?
Yes.
We can also do it after class if we want.
No. Don't. It will be very difficult to follow. Let's do it right now.
I can see that on your share screen.
No. I mean, yeah, that's fine. You can download later. Okay. You will need the files now, so please download it. Okay.
Do I need to leave?
Sorry?
Do I need to leave?
You said, do you need to leave?
Or
Why do you want to leave?
go to MyTSU.
But why do you need to leave the Zoom meeting? Sorry, Michael, I didn't understand what you're asking.
He thought he can do it. He want to do it, I think, by himself.
Okay, I'm following, but can you all answer this thing?
Yeah.
So, Mr. Nathan, I have MATLAB installed already, but the toolbox kit, whatever thing, I don't have that one
That's
installed.
okay. That will take only a few seconds. I will tell you how to do it.
Okay.
Let's just wait for everyone to answer. So there is one person who has not started installing. Please, whoever that is, you still didn't get the email from MathWorks? It only takes a minute or two to come. Okay. Still not all of you have, answered the question. Oh, so 8 people have, okay, now you're answering. Okay, so several of you, most of you, either you have already installed or you are installing right now. So who has not yet received email from MathWorks? Who is it that you haven't yet received an email from MathWorks? Usually it just comes in 1 or 2 minutes. Hello, you're all there, right?
I'm on your share screen.
No, that's fine. But what I'm asking is, who has not gotten any email from MathWorks?
I didn't.
Did you go and fill their Tennessee State University and your TSU email?
I will do it. See you.
Yeah. Please do it right now. Who else? Please let me know, because if not, you won't be able to do the things we want to do today. Okay, so, and 5 of you didn't even answer, so okay. I'm not sure what's going on, but okay. Now, let's go over the theory, okay? So today we are going to discuss viscoelastic materials. So these materials are, they have a significant difference from the materials we have been discussing so far. So what are the materials we have discussed so far? Can you tell me, either on mic or chat? Anyway, what are the materials we have discussed so far?
Well, we had a wood one, right?
We started with aluminum, then we did like steel and wood.
We didn't do steel, we did wood, yes. We did wood, we did aluminum. Okay, I mean, it wasn't steel. That bar for torsion, it was, I also don't know exactly what, so no problem. mainly aluminum, wood, and some kind of metal. So, okay, so you all remember. So the one point about all of these materials are that they do not have a really, or let me say, under okay, aluminum, let's take aluminum. At room temperature, it does not have a significantly viscous component to its behavior. Okay, so what that means is, let me give you an example. Now, so you all at some point you may have tied a clothes line or some kind of line to hang clothes or hang other things, right? So you have tied something like that. So you may have used a plastic rope which is tied between two walls or two hooks or whatever, and then maybe you're hanging clothes or something there. Oh, okay. Okay, just a moment. Some of you are having internet issues. So then what happens after a few days, you will observe that this string is not straight anymore and it has started sagging, right? Then especially if it's some kind of plastic, then you will see that after several days, you can see a significant sag. And whatever you hung there, it may be there. Okay, so what's going on here? You didn't change the load, but then the deformation is changing with time. So you get what I'm saying? So there is a time dependent component to the behavior. Okay, so you have applied a constant load, but your deformation is going on increasing with time. So this phenomenon is called creep. Okay, in the same way, if you let's say I tie a string, a plastic rope between two supports, and I do something, I pull it, and then I make a knot here, and then it's tight and all that, it's very taut. Then I come after 2 days, now it's no longer taut, it feels loose, there is no tension in it. So what happened? So my deformation is still the same, but my stress has gone down with time. So this phenomenon is called relaxation. So these two fundamental phenomena, creep and relaxation, these are characteristics of phenomenon called, or material behavior called, viscoelasticity. That means the material is showing, in addition to showing elastic behavior, it also has a viscous component. So what is a viscous material? Remember, if you think of honey, let's say, then you put a blob of honey on an inclined plane, it's going to start slowly flowing, right? So when you apply a stress, what you get is a strain rate. So you don't get, you get a continuously changing deformation, okay? So what you get is a strain rate. Similarly, if you just keep a pot of honey sitting there, then you will not be able to generate any significant stresses. I'm not talking about pressure, but shear stresses. You cannot have any shear stresses, no matter how you put it. Let's say you contrast this with a solid. Let's say you had a block of aluminum like that. Now you deform it to take this shape. If you do that, then there is going to be a very high shear stress in the aluminum. But on the other hand, you take a bucket and you fill it up with honey. Now somehow you deform the bucket to go like that, okay? Now there is still honey at the same level. There is no stress in the honey. The only way that you can generate stress in the honey is by flowing it, okay? So in the viscous materials, stress is only responsive to strain rate, not strain. So there should be a continuously varying deformation, only that will generate a stress. So this must be very familiar to those people in fluid mechanics. So what is the stress strain law for viscous materials? So you write the shear stress is equal to viscosity times rate of shear strain. Okay. Viscosity times rate of shear strain. So this is the stress strain law. What was the stress strain law for elastic materials? One dimensional. Hooke's law. Okay. In contrast to that, it depends on the strain rate, not on the strain. This is viscoelastic material. Notice one more thing, that is this is viscous material. In the viscous material, let's say you have a blob of honey, then I incline the plane and it flows. Now if I make the plane horizontal, it's not going to roll up again into its previous shape, okay? That is the permanent shape now, or that's the final shape now. So what is a very important point to note here, whatever energy you have put in, it's all gone. You are not going to get it back. Contrast that with an elastic material where you have a spring. Let's say you stretch the spring to some extent. Now your energy is stored in the spring as potential energy, and when you release it, you can get it back as kinetic energy, or you can convert to whatever you like, okay? So your stored energy is completely recoverable in an elastic material, okay? Even for our aluminum which we have been studying, here is the yield stress, right? So before this point, anywhere you load it, then you can, when you unload, you can get back all the energy, and it will unload along the same path, okay? So this is the characteristic of elastic material. Whereas in the viscous material, you load it and it takes a new shape. You lost all the energy that you put in. So I hope these 2 points are clear. Key points. There is no time dependence in elastic material, and all the energy that you put in can be recovered. In a viscous material, the stress has a strong time dependence, and you lose all the energy that you put in, or in other words, all the energy that you put in gets dissipated, okay? So this is the key difference between viscous material and elastic material. Now, viscoelastic materials have both these characteristics. That means when you load it and unload it, you will lose some energy, but not everything, okay? And when you load it, there is an instantaneous response to your loading, but there is also a time dependent response. So there is a time independent response and a time dependent response. Those are viscoelastic materials. Okay, so maybe now if you have understood what is this property of viscoelasticity, can you tell me any example of viscoelastic material?
Well, the first thing was your hanger example.
Right, so that is a plastic. So generally all the plastics are, plastic is a colloquial name for polymers. So polymers by their nature are, most of them are at least a little viscoelastic. Okay, so yes, Michael. So any other example?
About stuff you can twist.
No, you cannot say like that. You need to specify a material, a certain
Spring.
material. I'm
You
sorry?
know, elastic material will be like spring or something you can stretch.
Yeah, but what I'm asking now is, can you give an example of viscoelastic material?
Clarification, Dr. Nathan. So a
Yes.
viscoelastic material will have both an elastic component on the stress deformation graph as well as a plastic component. So that would include most metals. I mean, a
Okay,
lot.
okay.
No?
So Lilani has raised a very important point, and let me clarify.
I was kind
So
of thinking metal a little bit, but I was thinking metal wasn't really elastic. Like metal is
yeah,
more like toughness.
Maybe
yeah,
like polymers. Like
that's right. We said polymers already. So yes, polymers. But let me clarify. Metals have metal viscoelastic component is very, very small. So viscoelasticity is very different from plasticity. Okay. So let me clarify. That is a very important point to clarify. Okay, what happens in viscoelastic material? Now, let's say I load a polymer. Okay. Now I'm applying some stress. So what happens to the strain? So I will get an instantaneous strain. Okay. This is strain plotted with time. Now I load it. As soon as I load, there is some strain. Okay. Then I hold the load. So if I look at the graph of my stress with time, I applied some stress and I held that constant. Okay, the strain will look like that. Now this phenomenon is creep. Now in a metal, what happens? I'm plotting stress versus strain, and then that looks something like that. But okay, now when you cross a certain level of stress, what happens is you get plastic deformation. Now that is different from viscoelastic deformation. Okay, so the common thing between both of them is that in plasticity and in viscoelasticity, in both of these you have energy dissipation. But the key difference is that the viscoelastic deformation is still recoverable. Even if you fully recover the deformation, you still get the dissipation. So you get what I'm saying? So let's say that you have polymer, right? So you don't go, polymer also has plasticity. Let's say this is the stress strain graph of polymer. Now, if I load it slow, it will behave like that. If I load it fast, it will behave like that. Depending on the speed that I load, it will have different curves. Okay, this is polymer. Okay, now maybe there is a point for each of these where it becomes plastic. There is. Okay, I don't go there. I stay within the elastic range. Okay, and I load, unload. As I do that, I will keep losing energy. Okay, in metal that won't happen. As long as you stay in the elastic range, that is not going to happen. when you go into the plastic regime, then you get permanent deformation, which is plastic deformation. Now, in viscous material, your deformation is permanent, but the mechanism there is something else. It is related to plasticity again, but that theory is much more involved than what we discuss in this class. We can discuss some other time. So if you are interested, you can read about Eyring's theory. So he will explain how viscoelasticity, plasticity, not viscosity, plasticity, they both operate at the molecular level. They both are arising from the same underlying phenomena. Okay, so this is something different. So what here I'm trying to say is, for a metal, don't go into plastic regime. Stay in the elastic regime. Load, unload, load, unload. You will keep on going along the same path. You will never lose any energy. Okay. Whereas for viscoelastic material, you load and unload, you will lose some energy in the elastic regime. And the difference is that you are getting back all the deformation, but still you lost energy. Is it clear what I'm saying? You get back all the deformation, but you don't get back all the energy.
How about mercury or chewing gum or slime?
The chewing gum is a great example. Yes, definitely chewing gum is viscoelastic. So mercury, no, I don't, I'm quite sure it is not. Okay. So when do metals start exhibiting viscoelastic behavior is when they are at quite high temperatures. Now, mercury is already liquid at room temperature. You can, but at some, I don't know what temperature. There is some temperature which is maybe somewhere around its freezing point, where sure, mercury will also be exhibiting viscoelasticity. For general metals like steel or metal alloys like steel and these things, you need to heat it up to around 70% or 80% of its melting point.
What about rubber?
One second. Before you start seeing any significant viscoelasticity. Now, again, Michael raised a very, very good point again. Rubber has very small component of viscoelasticity, not much at all. Rubber is in a category called hyperelastic. Okay. Now, rubber is very, very important. There are, okay, now we are going a bit deeper and deeper, but we better come back. Now, you have something called cross-linked polymers, okay? Cross-linked polymers. So so you can imagine long chains, and they are linked at some junctions by cross-links. So you can, those of you maybe who are from chemistry background, you know what is cross-link, if you remember those things, okay? Now, when they are at a relatively low temperature, there is something called glass transition temperature. Again, the theory, material science behind polymers, there is a lot. We are not going to cover here, but and again, I will say one more point, that is the material science and mechanics. These two fields are very strongly interconnected, but usually engineers are very much interested in, or I shouldn't say, mechanical engineers are very much interested in modeling the phenomenon that is going on. They are not so much interested in what is causing that phenomenon, like what about the material chemistry, or what is it about the molecular structure of the material which is making it behave that way. Mechanical engineers are not that interested in that part. That is the material scientists. But mechanical engineers focus on we know that it behaves in a certain way. Now, how can I model this behavior? Now, I'm not worried about whether this behavior is because of cross-linking. Okay, this I'm saying in a very crude way. Okay, nowadays there is a lot of overlap. Okay, okay. So I said at a very superficial level, but nowadays there is a lot of overlap. So now what Michael mentioned is, now these are cross-linked polymers. Now these chains, they are not that free to move at lower temperatures. They kind of have some interactions between them. Now you heat them up to a certain temperature where these interactions, local interactions melt, not the whole material, but only some interactions, they melt in coats. It's really like melting. Now these chains are very free to vibrate about. So now when you stretch, you can imagine this way. Now let's say that you take a piece of elastic cord, okay, you tie it between two ends, very loose, okay, very loose, just tie it like that. Are these two ends going to feel any force? No, not really. Now you start vibrating it really hard, so it starts vibrating like that, up and down, up and down. Now these ends will feel a force, they'll feel a pull from these. In the same way, when these polymers are heated up and these chains can vibrate between the crosslinks, they can pull at the crosslinks. So that's what gives rise to the elasticity. And that elasticity is very different from metal elasticity. That is called rubber elasticity. And it is also one more name given to it is hyperelastic, because generally for metals, your elasticity is up to about 0.2% strain or 0.02% strain. But for these, you can stretch it to, you have done it. You can stretch it to 3 times its length, it will still come back. So this is different, okay? But okay, now Lilani is saying proteins, nucleic acids, organic, like natural fibers. Yes, those are good examples. Now natural fibers, yeah, they do, as long as there is some polymeric component, which usually there is. So yeah, they do, but not all of them, okay, some of them. Now proteins, okay, now we are going into protein. We cannot exactly call it as a macroscopic material. You describe it at a smaller scale, like a molecular scale. Now at that scale, the theory of mechanics itself is different. So but you can say somewhat, yes. So that's okay. Okay, so we went off too far away somewhere else. Let's come back. Now these two, creep and relaxation, those are the two. But I hope the question was, viscoelasticity is completely different from plasticity. I hope these two things are clear. Viscoelasticity is very much exhibited in the elastic regime. You don't need to go to plasticity. You stay within the elastic regime, you load and unload, you will get dissipation, okay? I hope that is clear, okay. Muscle fiber, yes, great example. In our body, a lot of the tissues are viscoelastic, okay? Now there is another point. Primarily they are poroelastic rather than being viscoelastic. Now, okay, what's the difference? I can tell you very briefly, okay? Those of you who are in civil engineering, you know that you build a house on the ground. Now there is soil here. So if you didn't provide good drainage and whatnot, then as your water seeps off, then your house may settle down. So that is called settlement. So here the time-dependent behavior of the soil is not due to anything inherent in its own molecular structure, but it's just because the water in the pore spaces is escaping out. Okay, so that is the time dependent mechanical behavior, which is because of flow of the pore fluid, that is poroelasticity. Okay, so and very often it is hard to distinguish in materials whether the phenomenon is poroelasticity or viscoelasticity. So one way to do this is you measure the characteristic time constants. So for poroelastic, it will heavily depend on the size. So you take a small piece, then it will be very less poroelastic. So you press it, immediately all the water is gone or liquid is gone, finished. There is not much of the time dependent behavior. You take a big piece, now the fluid is going to take a while to travel, you get a heavy time dependent behavior. But for viscoelastic, doesn't matter, you take a big piece or a small piece, you still get the same characteristic behavior. Okay. Okay, now still we are still going far away. Let's come back. Now, okay, these two are the two main phenomena, creep and relaxation. Now, see, in one sense, no need to be, okay, now it's of course all of your personal kind of thinking and whatnot. So nobody is saying that we should only do this, or actually no one is even restricting us to science, okay, or even to reason. We human beings, we try to build everything based on reason, right? Now you can study some article, it was on the flying birds, how well they manipulate the convection currents, right, while flying, and how well they can optimize their flight path. Now they didn't use any supercomputer, or they are not solving differential equations in the air. So what did they do? They did something else. It's not even neural network. It's something, right? We don't need to be too narrow. Okay, so but again, let me say this also: if you are, since you all are going to be engineers, please. The word is not narrow, but please stay focused too. Don't. So I know you may have read some old story, like some person he was expert in physics and expert in what do you call this people who study fossils, paleontology, and is expert in. So don't go like that. Okay, that time is gone. In today's world, you have to. I'm not saying you have to be, but it's let's say safe to have at least one specialization. Okay, so keep that in mind.
What's these graphs of?
This graph is for strain. This graph is for stress with time.
For what material?
For any viscoelastic material. So what I'm saying is, let's say you have aluminum, right? Thank you. We come back, okay? We don't go somewhere to some topics, we come back. Now, you can go sometimes, but it should be very targeted. Okay. We are, all of us are engineers, not something. Okay, so here is aluminum. So you pull aluminum, okay? You pulled aluminum, right? Now you stretched it to some strain. and you hold it at the same stress. Let's say you applied a stress of 20 mega or 20 ksi, and you held it at 20 ksi. So it's not going to do anything. It will just stay like that. No matter you hold it like that for even few months, it's not going to change, okay? But you hold a polymer at 20 ksi, today it will be this much, then tomorrow it will be that much, then day after tomorrow it will go even longer. It will keep getting longer and longer and longer. You got what I'm saying? So that phenomenon is creep. So Micah, is that clear? Oh, she is gone, it seems. You muted yourself. Micah?
Yes.
Okay, that's
Can you
clear.
hear me?
And now I heard. Okay, thank you. So chewing gum, yes, chewing gum is a good example. The one of the examples where you can see this phenomenon very clearly. So those of you who cook very often, sometimes you may be using cornstarch to either in baking or in cooking some stew or whatnot. Now you put water, and if you apply a lot of force, it will feel very stiff, okay? But if you poke softly, then you can go through it. So this is a characteristic of viscoelastic material. So this is the third thing, that is rate dependence. That is rate dependence. So again, this is also very easy to see. You take a viscoelastic material, you punch it hard, it will feel very stiff. But you go and you press it softly, then you can go in, okay? So the stiffness depends on how fast you are loading, okay? Okay, so those are all the characteristics of viscoelastic material. Now, let's come back. Okay. Again, this was a bit, when you are in civil engineering, you need to worry about viscoelasticity mainly for concrete and for asphalt, okay? So the old concrete buildings, the older design, they did not think much about viscoelasticity. So some of the older buildings, they have large deflections after many, many years, okay? So for asphalt, it's very clear. So you use on the roads, and you know that you may have even seen that there is you can go, or sometimes in the summers you can hit one spot on the road, then you will see a depression, then you wait for some time, it will come back up, okay? So that is viscoelasticity, okay? So then how do you model viscoelasticity? Mathematical model. So this is something associated with engineers rather than material scientists. So based on this word is good to remember, phenomenological model, okay, material model. What does this mean? You are proposing this based on the mechanical behavior that you observe, okay? So what is the other way to propose a model? You can base it on the molecular structure, based on how the molecular structure is based on that you can predict how the material properties are going to behave, okay? So how the material is going to behave, what kind of properties it will have, okay? So so in this model, so what is this model? Basically, there are two fundamental components we use for material model of viscoelastic material. One is spring, one is dashpot. So spring is used to represent an elastic material. Dashpot is used to represent a viscous material. And by connecting them in different combinations of series and parallel, we can produce viscoelastic behavior. So this is what we do. William, did you have a question? Okay, I just...
So this model has one elastic and one and two viscoelastic, or one
Very
elastic?
good. Yes, okay. That's right. One arm is purely elastic. Two arms, they are, yes, they are viscoelastic. They are called Maxwell arms. Okay. So let's see this. And if you have just one elastic and one Maxwell arm, this is called a standard linear solid. So this is used to represent viscoelastic material. Okay. So what is the equation for spring? Stress is some spring constant times strain. What is the equation for dashpot? Stress is equal to some viscosity times strain rate. Okay. Now we are writing everything in one dimension. Actually, the equations are in 3 dimensions, but no problem. Now, you know that when the elements are in parallel, they all have the same strain. When they are in series, they have the same stress. This is quite straightforward to understand, right? So when different elements are in parallel, they are all constrained to stretch or contract by the same amount, right? So the strain will be same when they are in parallel. When they are in series, you cut anywhere, you will see the same force from the free body diagram. So for series, the stress is same. For parallel, the strain is same. Okay. So now you can write the total stress is stress in the arm 1, stress in the second Maxwell arm, plus stress in the third Maxwell arm. And the strain is same for all of them. Okay. So now what can we write? For the spring element, you can write that. Differentiating, you write that with respect to time. Now, the strain in each Maxwell arm is the strain in the spring plus strain in the dashpot. So you can write the same for the strain rates. And you can write, simplify it in this way now. Strain for a Maxwell arm, this is true. Now, the stress in the Maxwell arm, or just this equation for the Maxwell arm, you can simplify like this. Just take multiply throughout by k, you can simplify like this. Okay. So now in the model that we developed, or I showed here, is called V-chart model, Wieding. So the total stress is stress in the elastic arm plus stress in the first Maxwell arm plus stress in the second Maxwell arm. So each of the Maxwell arms follows this equation. So now you can write, okay, so these 4 equations are what represent the constitutive law of the material. So you can see it is not a simple form like Hooke's law. It is in the form of differential equations. Okay, so this is the constitutive law of the material. Now,
could you hold on there for a second, Dr. Nathan? Okay.
Yeah.
I just want to. I know this is on our notes, but what page is this? That way I can just. Is the page number at the bottom here?
Page 3 of the page 3, equation 1.
But isn't it not so equation 1 is all 4 of these parameters,
Right.
all
That's
4
right.
of these
That's
expressions?
Right. That's right.
Okay.
Are we still talking about like this is our spring day, or do we switch over to something else,
Are we still talking about what?
like spring behavior?
No, so you can see there are both springs and dashpots, right? So that's how we generated a material which has both elastic and viscous components to its behavior.
So how do you distinguish between the two Maxwell components of the equation? I mean, I realize this is a graphical representation of what
The
you're talking about.
schematic.
Yeah, a schematic. So KM1 and KM2 are both Maxwell, but they are both viscoelastic, right?
That's right. So what is the, yeah, so Lilani asked a very good question. Let me explain that. So if you, there is some phenomenon involved with the relaxation. So when you study the stress relaxation, let's say you apply a constant strain and you see how the stress is dropping. So it looks something like this. You will have a few regimes. So you will have initially stress versus time. If you observe, initially the stress drops really fast and then a little more slow and then much more slow. Okay, so it will not be one exponential curve. So you can see a few types of behavior there. So one Maxwell arm represents a fast relaxation, one other Maxwell arm represents a slower relaxation. You could have as many Maxwell arms as you want, depending on how many characteristic times of relaxation are associated with that material. So is it better now?
Okay. Okay.
Okay, so from all those differential equations, so we see that it's much more complicated than Hooke's law. But the way we can simplify it is take everything into Laplace domain. Okay.
You do K times N.
I'm sorry.
Do K times N
K times N.
for the Maxwell.
No, that is eta, not N. No, there is no K times eta anywhere. K divided by eta is the characteristic, or eta by K is the characteristic
I think he means
relaxation time.
I think he means the K of M1 and the K of M2. I thought it was K times M as well in the equation 1.
I'm sorry. Yeah. Thank you.
K sub N.
Yes. It is subscript, not multiply. Michael, you should say thank you to Lillian. Okay. So when you do Laplace transform, so your 4 equations transform like this. Okay. Because in Laplace domain, the Laplace transform of the time derivative is just s times the Laplace transform of the variable. So then you can solve it to give a nice equation like that. Now this looks like Hooke's law. So when you write the stresses and strains in Laplace domain, now it looks like some form of Hooke's law. Okay. So there is one particular case of relaxation. Relaxation means you hold a constant strain. That means strain rate is 0. Under this condition, you can solve those 4 equations very easily to get a closed form relationship. Okay. So in this experiment, what we will do is I already collected at some point of time relaxation data and creep data. We will use the relaxation data to calibrate the material model. That means we will fit relaxation data and we will find what is the value of KE, KM1, KM2, which best fit that data. Okay. Once we find that, we will predict creep. Okay. We will predict creep. So that way we know we are validating our model. Okay. So first step is calibration using relaxation experiments. Second step is validation using creep experiments. So I hope you are all listening, because all this thing is definitely a little more complicated than the elastic behavior we have been seeing so far. Okay. So hopefully by now MATLAB is there on everybody's computer. Can you all start MATLAB? I will also start.
So we just need like the last equation then on this.
You don't need any equation. I already coded everything. I will just tell you. You just need to use the codes.
You say that again?
No, you don't need to solve any equations. I've already coded everything in MATLAB. So you just use the code. Okay?
Okay. Well for the lab report, won't we need to put these in?
Yeah, no need to solve. You just put the results.
No, I mean like for like the theory part of our lab report, won't we need the
Theory part, you can just do copy paste of
like the very last one?
no, not the last one, just the beginning. Let's see, maybe up to here, not before this, everything up to here.
Is the code in your file?
Huh?
Is the code in your MyTSU file?
Yeah, that's right. So now all of you started MATLAB? Have you started already?
Not yet. I mean, it's giving me some sort of issue. Hold on, please.
No, no, that's okay. So
Okay.
anybody who
It's
has
showing-
issue, please share your screen. I will help you.
Why is it trying to go to Citrix?
No, it shouldn't be going to Citrix. Maybe you can share your screen. I will try to. Let me stop sharing my screen. So whoever is having issue with MATLAB, please share your screen and I will try to resolve it.
We need to open a file that you sent in MATLAB or something?
That's later, but first did you already start MATLAB? Then you're good. Anybody who has not been, your MATLAB is not starting up, please let me know. You share your screen. I will tell you what to do. If it's already running, then you're okay. Just hold on.
So where do you put the code in your file?
Yeah, we are coming to that. All of you, MATLAB is up now? MATLAB is up and running?
No, I think I had a different version on here from some time ago, and I don't know if it's uploaded. Would it be possible for me to just follow the instructions you give and
Yeah, that's fine.
play?
That's
Because
fine.
I normally when you're going kind of quickly, I usually miss a step. So
Yeah.
I was really trying to get it open.
Okay.
But I don't want to hold up the class because I think class is technically almost over. So
Yeah.
I think
So we can, I mean, today I will just, that's why I was thinking, let's just do the setup next time, because analyzing the files, it will take a while to go through that, understand what's going on. So for today, let's just make sure everybody's MATLAB is up and running, then we leave and come back next time.
do you think it would be possible for us to maybe hit up MATLAB through Citrix, through one of the? Because I know I have it on here. It threw me some sort of message.
That's a good idea. Let me try. It is actually, yeah, that's right. I actually never thought of that. So that's a good idea from Lilani. So does it work, Lilani?
I know know for certain that I have the software on my computer. I just haven't used it in a couple of years, and so it threw me some sort of message about upgrades, and I need to play around with it. But to quickly get this done, I think I would probably try it through Citrix like I do with Abacus.
Don't worry, we are not going to do it today. We just want to do the setup today. Make sure everybody is having MATLAB, and then if everyone is already having, then make sure everyone is having curve fitting toolbox.
My MATLAB says 2019 version.
Okay.
One that I used it in.
That's fine. Actually, anything after 2000 should work, I think.
Doctor, I have tried before downloading the curve fitting toolbox because I had to use it for a different class, and it won't let me, like, it says download, and then I went to the tab where you actually download, and when I download it, it will say run or extract, and then when I extract it, it won't even open it. Like I have tried. Okay, I can share my screen. Let me open up MATLAB first. But I have tried
like this, anybody. So make sure MATLAB is up, working on your computer. Make sure the curve fitting toolbox is working. Okay. So anybody for whom this is not working, let's get it resolved today.
Where is the?
So that next class, yeah, I will tell you. So that next class we can start working. Okay.
Where is the curve fitting on MATLAB so I can look at where it is, I guess.
Okay, so Mihret, just give me a moment. I will share my screen just for a bit to show Michael, then you can share. Okay. So go to apps. You can see here curve fitting. So go to apps. Michael, go to the tab called apps. Then click on curve fitting.
There's an app. What I actually had to do was just type CCT tools on the command window and it will open up. I didn't know actually
okay.
I'm not sure if there's another way of doing it.
So it works.
I'm not sure. Let me try it because before it didn't work for me. I didn't know if it has an app on the MATLAB itself.
Okay.
Can you show us again?
Yeah, sure. So
how to get to the curve
this
fitting?
is MATLAB. It must open up in the Home tab, but you go to the Apps tab and click on curve fitting.
No, if I don't have that.
You don't have. Okay.
Yeah.
Okay. So then click on Get More Apps. Then it will open this add-on explorer, and then in the search type curve fitting. And here for me it says already installed, but if you click here it should install.
Okay. Okay, thank you. I'm about to install it.
Okay,
how long does it take?
It should just take a few minutes or less. So anybody else having issues?
Yes, whenever I click on get more apps, it doesn't go anywhere, I believe. It's just hanging there.
Okay, let me stop share. Ali, can you share your screen?
Are you able to see my screen?
Yes.
Right now you are able to see my
Yes.
MATLAB is open?
Yes. So click Get More Apps. Oh, I see. So the shortcuts file has been regenerated to the default due to corrupted. Can you click there on the command window? Type CLC. CL No, CLC.
L. Okay.
Yeah. Enter. Okay, now type, click get more apps again. Did you click?
Yes.
Okay, so, oh wait, I think there is something on your computer that is stopping this from running. I don't know, something like a firewall or antivirus or something. You know what I'm saying?
No, I do
think
not have
so.
antivirus in my laptop.
Or maybe a firewall. See, because something is not allowing this to run. Okay, let's try one thing. Can you close MATLAB?
Yeah, sure.
Then you go to the MATLAB. Where is MATLAB installed? Go to
Well,
the
I have it in
installation.
my desktop. You want me open it again or go to the C?
No, open. When you open, right click and run as administrator. Do that.
Okay, got you. Doing it right now.
Okay.
Sorry. Come on.
Yeah, that's crazy. Okay, there it is. Now
What's
type
called again?
I'm sorry?
So, fitting.
Curve fitting. Yeah, this one, yeah. Click.
All right, thank you so much.
You're welcome. Okay, anyone else has issue? So you should have MATLAB and curve fitting toolbox.
Okay, so my MATLAB, it took me online, and it's saying from the company that I do not have a license.
You don't need, actually, as long as you're a TSU student, that's enough.
Activate your software and contact your MATLAB administrator.
Can you share your screen?
Okay, I can try.
Oh, okay, wait. Mihrat is sharing. Just a moment, just give her a moment.
Okay.
My problem is I say that I have tried it before installing it, and after I install it, when I say run or extract or something, it won't, like, it just won't open it. But yeah, I have tried installing this curve fitting tool before because I had to do it for my major in lab.
Oh, okay.
So I don't know if you can use the remote desktop to do it. I'm not sure if that one has it.
No, you don't need remote desktop. Just click get more apps. Let's see what it does. Did you click on get more apps? Mihir? Yeah, now wait for a moment.
Yeah, it's coming.
Okay.
Yeah, it's okay. Okay, Dr. Nathan, yeah, it's taking me through a path where I have to get an activation key.
No, you shouldn't need all that. So you did, it should just send.
So with the file that you sent us, I should be able to install it with the file you sent us. So I may have to uninstall the version that I have and reinstall what you sent us. because what it's doing is, I don't know if I can share my screen yet, but
Is this the one? Because I searched up curve
Wait,
fitting.
wait.
shoot.
Okay, just wait. So for Lilani,
Yes.
you went to the mathworks.com, then get MATLAB, then you put Tennessee State University and your TSU email ID there, right?
No, what I did was, shoot. Can you hear me?
Yeah.
What I did is I basically just downloaded the file you sent because I already had a version of MATLAB, thinking that it was still working from a previous course.
Got it.
But it's not I think I need to uninstall that version and reinstall.
Yeah, just uninstall that version, then you follow the steps I gave. Go to mathworks.com, get MATLAB.
Okay.
Then, all of that.
Okay.
It shouldn't take very long.
No, that's okay.
Yeah. Okay, so let's, Mihiret, what happened after you clicked get more apps? Hello, Mihiret? Hello, Mihiret?
Yeah, I was trying to unmute myself. My mouse like won't go up like that.
Okay.
Okay, so install, right? So I'm gonna install it. It might take a while time.
Oh, so so it's installing.
Yeah, I have installed it before and it won't work. I mean, after I installed it, it says run this application. Then I run it, and
But now it works.
But let's see. I mean, it will install, but then opening it after that is the problem.
Okay, but you don't see it on the list of apps. You should see it.
What do you mean?
See, in your apps right now, you have classification learner, regression learner, distribution fitter. You don't have a curve fitting app there. If it installed successfully, you should see a curve fitting app there.
Okay. Okay, so we're not supposed to open it by itself. It will show up on there.
It should show up, so just wait till it finishes. Okay, anybody else has any questions?
Just for clarification, so I can go directly through Google search and look for MATLAB and try to download a student version?
No, then it will it won't. It will ask you for a license, then temporary something. Also, just use the TSU one because you are getting access to it through the university. So
okay, so go through Banner and include it the same way we did Citrix.
No.
I think you're supposed to go to MathWorks.
MathWorks. Okay.
Let me show you. I sent an email.
The email that I got said please install MATLAB. I didn't see further directions on there. Let me.
Oh really? Okay. Yeah, here, it's there.
Okay, under the Zoom link or for today, please install MATLAB.
Let me share my screen.
I have sent it to you, Liliani.
Okay, for Tennessee State under enter your TSU. Okay, I see. I'm sorry. I apologize. It got buried with your response to me. Yeah.
Right.
Okay.
I do that too. Yeah. So.
You will get a link down here. Okay. All right. Let's try this again.
Okay, so while Lilani is doing that, everyone else is clear. It's fine. Running the curve fitting toolbox, everything is done. Because we need to do it next class. So I hope everything is ready and working.
Mm-hmm. Would you mind letting us know any of the apps, making sure that all the apps that are on there that we double check? So just
Just the curve fitting is enough for this lab. I mean, the others, it's up to your interest. Like you may need something for other projects or other classes or something else. So that's up to you. But for this lab, we only need curve fitting. Melanie, you are still there?
yes, I'm still here.
Okay.
Yes, thank you.
Okay. So if no one else has any question and everyone got MATLAB to work, everyone has curve fitting toolbox installed there, then we can end the meeting.
Is there like a lab report and a curve fitting both?
No,
Is like
no, nothing today. Next time.
I'm trying to download the curve fitting toolbox, and it's telling me to shut down the running MATLAB.
Probably wants to upgrade.
Can you share
You
your
have to
screen?
shut down. It will shut down any of the system you're using. That's why I'm just waiting until everything is done or Zoom is over, because it will shut down everything you're using on your computer currently. You have to save your work.
Okay. I have not, maybe you're right. Could be. Because I installed it a while back, so I don't remember.
Yeah. Are you planning on doing a confusion session this Friday? Then maybe we can play with this and make sure.
Yeah, last Friday, nowadays the Fridays have become so tight.
Yes, that's okay. Okay, I'll just email you
Okay,
you usually you're really good with responding. It's taken me through it, so if I have any issues, I'll just email you. Thank you.
Okay, sure. But I'll try to have doubt session. Okay, so then we can end the lab, okay? All of you, please make sure you have MATLAB and curve fitting toolbox by next time. Okay. Thank you. We end for this time, okay? See you all next time.
Mr. Nathan,
Yes.
for the other labs, we have what were we doing last week? The
Torsion
simulation for
simulation. Torsion simulation.
When do you want us to turn that one in?
That was due today.
Oh,
But
okay.
okay, you can work on it and submit. The Dropbox folder is there. Just put it.
Well, you said it's informal. We just needed to comment on the images. I think you gave us S13 and S12, and you are three.
Three, yes.
Okay.
So
And just comment on it.
Verify the angle of twist, compare it with the hand calculation, and also compare the shear stresses with the hand calculation to see how well it compares. That's all you needed to do.
Okay, so with verifying the angle of twist and verifying the stress, are we using the same tool that we use to measure the length?
No, you can just look at the angle of twist on the legend. That's enough. You don't need to use.
Oh, okay. So the legend that comes up with that image.
Right. I know that's approximate, but it's
okay. Okay, perfect. Yeah, because I sent you all 9 pictures, and I'm like, what is this?
Oh,
I mean, I sent you all 9 images in the email that I sent you when I wanted clarification for what U versus UR were.
Oh, you did.
Yeah, because it looked a little odd. The stress stuff looked fine. That looked like what we looked at last week. But the angle of twist for under the URs and versus the U's were a little odd looking. So I'll send you my report this evening. I just wanted to clarify that. But
most of my URs were blue and purple.
Yeah, I know. So there was, if you remember, we did discuss that there is something we need to improve in the model with respect to the boundary conditions. because the twisting is a bit localized to one end. It's not really uniform, but we said for this report, we just go with this model, and I will try to, yeah.
Yes, because when you look at, when I turned the model longitudinally, like looking at it longwise, it almost looks like a flute instead of just a cylinder.
Right,
And I was like, why is that doing that? That wasn't.
You're right. So there is
Okay.
something off with the boundary conditions there, yes.
And are we looking at the end that would be the biggest end? Because
Yeah,
it's
yes.
okay. All right,
Yes.
then that's all I needed to know. Because I was like, I don't know what this is. I thought it was a cylinder.
No, you're right. There is something going on there. If you don't want to get confused, then you can just use plot on undeformed shape, but you can change the option to plot on undeformed shape. So go to contour, then, or I think it is plot contours on undeformed shape. So if you do that, then it may be less confusing to see.
Okay, thank you. Yeah, I could. Those images I sent under UR were all under underformed. That was, I think there was an error somehow with the way it was saved. Because
no, you're displaying the default option, which is plotting on deformed shape. But if you plot on the undeformed, it may be a little less confusing.
Okay, thank you.
Yeah, sure. Okay, so now everybody please have MATLAB curve fitting toolbox by next time, okay? Okay, thank you. We'll meet next time. Okay?
Have a wonderful day, sir.
Okay,
I'll
you too,
email
Ali.
you if you
Thank
have
you.
any problem.
Yeah, okay, no problem. Sure.
Thank you.
So how do I save the video? Just stop and is it going to save on my computer?
Yeah,
did
we'll
you
save
do?
it on your computer.
It should be there if after I end.
There's gonna be like a curve fitting lab report.
No, Michael, we need to do it next time.
I mean, I was talking about next time, not this time.
Yeah, next time